Hello, Dr. Sanders. So for our final graphics project, I'm in the team that is doing the black hole ray tracer rendering project. So I'm gonna go over specifically what I've worked on for this project. And so for the for loop that we see here is what we're doing is we're iterating through each particle that we are considering, and this particle count is exactly 60,000. So this is the amount of particles we want to generate within our black hole. So this is particularly useful when we're trying to render a specific accretion disk. So what I mean specific is by doing region choice, we do a math random float of R, and this essentially is what we're doing is we're using the region choice that we're getting from random and the preset of W1, which is the width of the first ring, and we are doing we're starting to initialize specific data we're going to pass to the kernel, and specifically here we do a W for math.random, same like we did here, region choice. Here we do the radius of the first ring. Essentially our black hole has two rings that we're trying to render. And the first ring here, we do a math square root of the first max of the ring times the um, average of the max and min. So that's why we subtract these two while multiplying the min. So essentially we're trying to get a brief, like a, what do you call it? A boundary in which we want to set the ring in. So that's essentially what this is doing here. And then else, if we kind of just want to do a specific the other ring, the second ring that we want to generate, then we do the minimum and maximum um, what's it called of the second ring that we declare here in U. So essentially it's the same equation. So we just pretty much set a boundary in which we want the accretion disk to render. So this is the equation that we use, and yeah. So here we just have a preset values that we want to pass in specifically to the kernel. So this is the rendering particle kind of angle. So we use this to determine in which part of within the black hole, what would be the angle of each particle. The height is the thickness, and the px and py and z is specifically the coordinates for the particles. And then speed is the rotation in which we see this particle doing, and then the velocity of those particles within the given what is called within the given speed, and then the radius column. And sorry, not radius. It's just the red column and green column. So this is the RGB, or not R. It's just the RG. We're not passing any B because we essentially just wanted to do specifically red, and in this case it is red. So 1.0 float represents a 255, in this case in green it's 0. So essentially the RGB colors that we're passing is a 2555 dot 0 or comma 0 comma 0. So that essentially makes red, and then these are the parameters in which we pass, and we create an array, a vector, and this vector will contain the particles that we want to pass into the data. So this would be the positioning of the particles, the velocity, and the color that we want to pass in with the RGB for the specific particles. And once that happens, we return, and then we set in the main the width and the height. So currently what we were aiming for is a 2K resolution. Here we are initializing J-coded drivers, making sure that we enable debugging. So this is essentially what these two lines do. This device essentially gets our GPU access and sets it up as a device. And this just has 0. So yeah. So this is just setting up a device, making sure it's able to communicate. Context is the kind of the data we're going to want to pass in later on. And then we pass in this here. So this is the initialization between the device and what we're expecting to pass in. And then here is the, what's it called, memory usage that we want to set. So imagine this as a vector size, sort of. and this is just limiting the GPU memory usage here. Then the module is the way we're going to communicate with this. So essentially, the kernel that we're going to be passing in. Here we are loading in the compiled kernel. So this should be a PTX file. Traceray kernel is the implementation that we're trying to implement with the ray tracer. So essentially, with the kernel, we pass in this, and this is able to communicate with the .cu file. So in this case, actually, it would be the PTX. So in PTX, it looks for a specific like method call. So this method call would be traceray, and it would be module, and it would be called this in the PTX frames we want to pass in. So we essentially want to generate 150 pictures. So this is what the variable pretty much set. And then frame, here we're just kind of iterating through every single frame. And for starting at 0 frames, we're going to set the camera and get the camera at frame. We have a preset vector, like not a precompiled, but a set scene that we want the camera to follow. So this is essentially how we get that data. And rendering on GPU is the ability where we're passing in the OBJ file specifically into the, wait, oh no, this is render on GPU. So this essentially is the method in which we call, where we start creating the parameters of the kernel for GPU, for the CUDA, so we could communicate with JCUDA and our GPU. And then here is our image data. So this is where we store our results in an array. Then JCUDA driver CU memory. So we're just copying memory to the driver. So this is driver to hardware. So essentially what we're doing is just passing the data into CPU to the GPU here. So we're passing a pointer image data. So we're passing the data of the individual in the single image. So so this should have the total RGB colors of the image, the output, in which this is kind of like the device we're using to communicate with the CUDA, and then width times height is the overall area, and yeah, so we're essentially creating a memory to the size of the width and the height. So that would be the total pixels in between the 2K. So I don't know how much that is, I guess. That'd be a lot of pixels though. Buffer image, let's see, buffer image output. The new buffer image width and height. So this essentially is what is kind of rendering each image and giving it as is kind of setting out the output. So essentially this is the final result with the ray tracer embedded in it. So here we do for every Y, and we're just drawing every RGB that we get from the kernel. So here we just pass in where we want to store it. Here we're going to be storing it by frames. So we're going to start off at 0, 0 and slowly increment that. And then image.write would be writing a specific file. This is going to be an output of a PNG with a file name um, based on this here. So yeah. And then we just do a debug message saying that we saved it. JCUDA trait CU memory. So this is the ability where we're kind of trying to optimize the GPU usage here, where we're freeing data specifically being generated by the D output. And just to go over that again, D output is the one in charge of generating the final results for every image that we iterate through. And then, yeah, so this is just a catch error if there's any errors between the rendering process. Here in JCUDA, we find that we were trying to implement the optimization of freeing memory for the background and camera, but we kind of ran into issues with that. So here, running on GPU, this is where I mentioned earlier where we're kind of initializing the kernel parameters here. So here we create a pointer. A pointer is in which we use for the communication between the GPU. So these kernel parameters are what we pass to our compiled, no, sorry, this is the variables that we pass to our kernel. And then here we allocate the memory in our GPU, which is the output, which is the image, width times height times the size of it. So this is the overall area of the images, or no, sorry, of the resolution. So yeah, so that's that. Then camera data. So what are we going to pass to the GPU? Well, what we are going to pass is the position of the camera, which is the X, Y, and Z coordinates, and then the forward like mobility of the camera, so the X, Y, and Z positioning, as well as the right camera and then the up camera. So essentially what the right camera does is just like a specific look at, and then the camera up is the specific uh, where the camera is locating or like looking towards, and then the FOV, yeah, so it's just field of vision. That's pretty much what it is. Buffer image, BGL, see. So here we're going to start implementing the background of our code. So the star PNG file, or JPEG in this case. So here we start getting data for it. So we need to send this type of data to the kernel. So what we will be sending is the background width and height, and then the background pixels. So this is could be done by just multiplying these two, and then we're storing it. And then here we're just storing every individual pixel within the resolution. So here we just do that. And then this is the array particles. We generate particles, which is a method that we go over later. Then background. I guess I could go over it. Generating particles, a brief overview is pretty much just like uh, the individual component that we went earlier. So actually we did go over this. So this is the particle generator here, this data here. So here we go down, background image, so we get the RGB coloring, and then we also pass in the height and the width, and then so we're just getting in each individual RGB based on the image. And then here we read, and this is specifically for the OBJ file. So here this is the texture mapping of the individual interstellar OBJ. So the way we do this is we get the texture width and height. Same concept that beats for like the background. Same knowledge that we implement here. The only thing we just pass in differently is the texture width and height, but the math that we use is pretty much the same. Here we create specific devices for our specific allocations for what do you call it, for our variables. So we need to create new devices for each individual like major part of our code. So here we could find that this line here, we create a new device specifically for the interstellar OBJ. So we pass in the device, we name this dtexture. This device will then kind of help communicate with our kernel, saying that there's a valid device, and what we're going to be allocating to the device would be the device name in which we're communicating here, the parameters that we want to pass in. So this is the size of the parameters, and then here we just do a allocation, like the initialization of the allocation between the hard drive, or sorry, to the CPU and to the GPU. So yeah, so that's the same thing here. And then specifically here, we're doing camera data, same concept, data allocation here, passing that data allocation, the size, oh, I'm sorry, the size of the data allocation and the type of data we want to pass into that device. And then here we are doing particles, specifically particles. So again, just the device name, the allocation, and then the passing between the CPU and GPU. And then we also do one for the background. And then um, we start our initialization of our kernel parameters. So we start here. If we want to use a GPU loader, which we do, and this was just for debugging purposes, but for our final, this is our main kernel here. So here we pass in the model data. This model data is essentially the OBJ loader, and we pass in the triangle data. So the way we map it is we essentially draw triangles in the individual OBJ to help with the texture mapping. And then the text coordinates model. So this is the text coordinates that we have stored here that will help with the mapping of the OBJ file. And then this is the triangle count. So the triangle count would be the amount of triangles that we want to set for the specific OBJ file. Then the device here, we pass in a D triangles. So we want to pass this into the kernel. So this is essentially the amount of triangles that are around the OBJ file or that we want to have wrapped around. This will help with like mapping. And then here the allocated D triangle data length. We just essentially doing memory allocation specifically for the mapping of the OBJ. So the reason why we have this here is because if we find that we want to use an OBJ file, then we want to allocate a new device that will pass in the texture triangles to the kernel. And then here we have basic variables here that we are going to declare. So here by the event horizon radius, we're going to be using a 7. This is actually based on the this guy's name. I don't know how to say it, but that's his name. Radius. So we did try to implement real formulas to this code, but the scaling was sometimes a bit too large for what we wanted, so we kind of had to descale it. But essentially the event horizon is 7. The max distance in which we want the ray tracer defined, or the max distance that we want the ray tracer to kind of travel, is 10,000 floats. So here we find each individual step. So for every individual particle, this is the amount of steps that we do for ray tracer. So essentially this is how we check if ray tracers have been hit by the rays that we sent out, or if they didn't. So yeah. And then here the step size here is a step, I guess like this will help pretty much with the rendering of the accretion disk later on, as well as the GM gravitational mass. And then, okay, so this is where we start passing in the data. So all this that you see here that I have highlighted is essentially what we have slowly been working up to. So all of this that I went over is essentially like just passing in these variables data. So we could use later on in the kernel. And then here is else. So the only difference between this kernel that I have highlighted and the one here is that we ignore the texturing of the OBJ file. So here we are kind of avoiding passing in the texture file mapping data. So yeah, because we don't want an OBJ file for some reason for our debugging, this essentially is what we create as a parameter for our kernel. And yeah, this was a very long explanation, but essentially this is what we did or what I did for my programming part. But yeah, and then I'm going to showcase the video. So in 2 seconds, you'll see the video that I actually compiled. So thank you, Dr. Sanders.